So, hello everyone. Today we'll try to do some examples on strain energy method, deflection of beams by using strain energy method. So, we'll try to do some examples on strain energy method. So, here we need to find out the deflection of the deflection of the beams at the required points. Let's take one example. So let's take example this example. So, determine the deflections at the load point where the uh, load point for the beam shown in figure using strain energy method. So using strain energy method, so this is a given problem. So what you have to do, we need to find out what is the deflections under the point. See, under the point load, we need to find out the deflections under the point load by using strain energy method. So strain energy method. So here here this is a given problem. So as soon as you see the problems, your first step is to find out the reactions. So we need to find out the reactions. So for that, let's redraw that beam diagrams. So let us take this point A and B, and these are reactions RA and RB. I taken as sections at different this AC portions and BC portions. Guys, please, from these two portions I taken the sections. For AC portion, let's take a sections at a distance x from the point A, and here similarly for BC portions, let's take a section at a distance x from the point B. Now so let us find out the reactions. So let us find out the reactions for that. So once again I will read the diagram here. So once again I will redraw that beam diagram here. So beam diagram here. So it is roller at these portions. So 80 kilonewton is acting exactly at the center. This is point A and this is point B. So let us take reactions RA and this is RB. So moment of inertia for this AC portion is I, and this portion is 2I, and this is 4 meter and this is 4 meter. This is 4 meter. So we need to find out reaction first. So and here also I taken sections for this sections, AC sections from X, and here also I taken one sections X from point B. Like this we need to take sections. Let us find out the reaction first. First step is to find out the reactions. What is the RA? RA that equals to RB, that equals to total load divided by 2. Why? Because it is symmetrical, you can see. So if you cut exact at the center, left hand side equals to right hand side, 4 meter 4 meter. So I can directly take 80 divided by 2. So it is 40 kilonewtons. So it comes to be RARB equals to 40 kilonewtons. Now our next step is to find out the movement at these sections. Your next step is to find out the movement at these sections. You need to find out what is the bending moment in AC portions. What is the bending moment at a section? At a section we need to calculate. Similarly, you need to calculate what is the bending moment at these portions. Okay, in BC portions at a axis distance, what is the bending moment? We need to do it. The same thing I'm doing it here, guys. Please let us calculate what is the bending moment at this one. So mxx in AC portion equals to what is the bending moment at AC portions? Bending moment at AC portion equals to RA into X. So RA into X. So what is RA? RA is 40 into X, that is equals to 40x. Similarly, calculate what is the bending moment at BC portions. In BC, so you need to calculate what is the bending moment in BC portion. So BC portion equals to what? RB into X, that equals to 40 into X, that equals to 40x. Because it is symmetrical, so we'll get the bending moment in AC portion that equals to the BC portions. Now let us consider strain energy due to bending for the beams. So what is the strain energy due to bending? U equals to 0 to L m square by 2EI into dx. Now please, you need to find out, your first step is to find out what is the strain energy in AC portions. We need to find out what is the strain energy in AC portions and what is the strain energy in BC portion, and we need to add both total strain energy in the whole beam. So now let us consider this. So how to write? U equals to 0 to 4. This is for AC portions. What is that? mxx by this is m square, so by 2ei into dx. This is for AC portions. And for BC portion 0 to 4, you can check here for BC portion what is the moment of inertia given. Moment of inertia is 2i. So you need to take care. So 0 to L, so m xx square divided by 2 into 2ei. Please remember guys. So here moment of inertia for BC portion is 2i is there, so 2 into 2i. So now let us integrate this. So let us integrate this. So u equals to before that you substitute the value of mxx. What is the mxx? This is 40 into x whole square divided by 2ei into dx plus 0 to 4 40 into x divided by 4ei into dx. So now integrate this. So I can write this one. What is that? So I can take out like 40 square divided by 2ei. You can take outside. So 2ei can take outside. So 0 to 4 x square into dx plus here also you can take outside. What is that? Here also you can take outside. What is that? 40 square divided by 4ei. So you can take outside 0 to 4 x square by x square into dx. So if you integrate this, you will get so this I will get how much it is. If you integrate it, u equals to so this is will be what this will be what 800 by ei. This will be 800 by ei into x cube by 3 0 to 4 plus so 400 by ei x cube 3 by 3 limit 0 to 4. So then what is that? So after that how much you will get? So we will get, so u equals to, so if you calculate, you will get u equals to how much? 1766.67 divided by ei plus 8533.33 divided by ei. So total you will get strain energy. Total strain energy equals to you will get approximately 2560 divided by ei. So we will get this one. Now what is our next step? So this is the strain energy stored in the beam. Total strain energy stored in the beams. I calculate what is the total strain energy stored in the beam. U equals to 2560 divided by 25600 divided by ei. You know that by using what now? By using law of conservation of energy. So now you can apply what is that? Law of conservation of energy. So now you can apply law of conservation of energy. What is law of conservation of energy? Law of conservation of energy, U equals to, so what is that? Strain energy or internal energy stored, that equals to the external work. External work is what? W. So what is U equals to, what is the external work done? External work equals to half into P into delta here. Half into P into delta. So U already you calculate what is that? 25600 divided by EI into of P. Here P equals to what is the point load is acting? 80 kilonewton is there. So substitute what is the 80 kilonewton? 80 kilonewton divided by delta. So here delta is the unknown. We need to find out that one. This is 640 divided by EI. This is how we need to calculate what is the deflections under the point load. So this is how we need to calculate what is the deflection under the point load. Okay, this is one example how we need to do the deflections by using how we need to find out the deflection under the point load by using strain energy method. Okay guys, so now strain energy method. Let us take another example. So let us take another example. So this example consider. Let us consider another example. What is that? Determine the deflection at the point low. Deflections are at the load point for the shown in figure by using strain energy method. By using strain energy method, guys, please. Here so this is a given problem. So here you can say you can take a equals to constant. So here a value remains same. It didn't given means you can take a equals to constant. A equals to constant. You can take a equals to constant. Now, so as usual procedures, first I written the diagram. So the diagram, you need to find out, the first step is to find out the reactions. So reactions. So and you need to take the sections from, let's say this is the AC portions. AC portion, let's take a one sections, and BC portion, let's take a another sections. Now let us calculate the reactions. So let us calculate the reactions. So so for this diagram, so I will do it here, guys, please. So let us calculate the reactions. What is the reactions? So this is hinge at these portions, and roller at these portions. This is point A and this is point B. So here, so this is point load is acting, how much it is? 80 kilonewton. At what distance? This is 2 meter, and here this is 6 meters. Okay, guys. So here we need to take a sections. So x. Here also we need to take a distance from these portions from point to C. This is x and this is x. So please remember, as soon as you see the problems, so your first step is to find out the reactions and bending moment at the sections. In AC portion, what is the bending moment, and BC portion, what is the bending moment you need to find out. Before that, we need to find out what is the reactions you will get at these portions, at the support RA and RB. So let us take this one. What is that? Reaction. How can you find out? Sigma Fy equals to 0. How we have to find out? So by using equilibrium condition, sigma Fy equals to, here you can see, compared to the previous example, this is not a symmetrical one. This is 2 meter here, and here to here 6 meter is there. So it is not a symmetrical. So use equilibrium conditions to find out the reactions. Sigma Fy equals to 0. Ra plus Rb, that equals to 80 kilonewtons. Then take algebraic sum of all the movements that MA at point A equals to 0. Take clockwise is positive, anti-clockwise is negative. So here, so RB into 8, so is rotating anti-clockwise, minus, plus 80 into 2, that equals to 0. Then RB equals to 80 into 2 divided by, so divided by 8. So RB I got 20 kilonewtons. Substitute in this equations. Let us take this equation number 1. Substitute in equation number 1. I will get RA equals to 80 minus 20, that equals to 60 kilonewton. That's how we need to find out the reactions. So now let us consider this. The same thing here, you can check here. So I got the, what is the reactions R and RB for the given problems. Now, for simplicity, we can now I draw one table like this. Portions, origin, limits, m-axis and EI. So better you draw the table for to solve the problem. So if it is unsymmetrical is there, beam sections are unsymmetrical is there, better you draw on table like this. So let us consider this portions. What is the portions? This is a beam. You can see AC portion are there in the total beam. AC portion are there and CB portion are there. 2 portions are there. So now I consider 2 portions. Portion like AC portions. So here, what are all the portions here? AC portion and BC portions. You can see this diagram. What are all the portions are there? AC portion and BC portions are there. Now, what is the origin? So here I taken the sections at a distance x from this side. Similarly, this for BC portion, I taken a section at a distance x from the support B. So similarly, for that, what is the origin? So what is the origin? So for AC portion, A is the origin, and for BC portion, B is the origin. So you can see here, for AC portion, A is the origin, for BC portion, B is the origins. Okay, now limits. For limits, what is the limits of those portions? So for AC portion, what is that? It varies from 0 to 2 meter is there, right? 2 meter is there, so 0 to 2. For BC portion, it varies from 0 to 6. 0 to 6 0 to 6, the same thing written here, 0 to 2 and 0 to 6. Okay, now movement at the x-axis. What is the movement at x-axis? What is the movement at x-axis? So here you can check here, what is the movement at x-axis? Ra into x, force into perpendicular distance at the AC portion, Ra into x. What is the Ra? So 60 kilonewton, 60 into x. Similarly, what is this? Rb into x. For BC portion, what is the moment at x-axis? Rb into x. So this will be, so what is Rb? 20 into x. Same thing I written here, guys, please. What is the moment at the sections? For AC portion, 60 into x, Ra into x. This is Rb into x. Then what is the moment of inertia at that point? Moment of inertia is same for those things. Now let's consider this. So let us consider this. Now we need to find out what is the deflections at point C. So let us consider what is the deflection at point C. Deflection at point C equals to what? So U, strain energy. You already know that what is the strain energy at different points. What is the strain energy at different portions we need to take. This is for AC portion, strain energy. Total strain energy you need to take. So integration of 0 to L m square by 2a into dx plus 0 to 6 integration for BC portion 0 to 6, limit from varies from 0 to 6 m square by 2a into dx. So same thing here. So what is m for AC portion? It is 60x. What is m for BC portion? Is 20x. So do the integrations. So please, you can see this is the integration, simple integration steps. So do the integrations. So I will come to know what is the total strain energy stored. U equals to how much? 19,200 by EI. Then by using law of conservation of energy, what is that? U equals to external work done. What is the external work done? W. What is W? W equals to half into P into delta. So what you got total strain energy, how much I got? 19,200 divided by EI into half into 80 into delta. So here P is given load, how much it is? 80 kilonewtons. So find out what is delta. Delta equals to 480 by EI. Please remember, guys. So this is how we need to find out the deflections. This is how we need to find out the deflection. I got delta equals to how much I got? 40 by EI. So please, whatever the sections here, so we need to sum up the strain energy in this portions and this portions. Please remember. So you calculate strain energy. It should be between 0 to L m square by 2 EI into dx. This is for AC portion, plus similarly you need to do it in 0 to L m square by 2 EI into dx for BC portions. So you need to do it for two portions. So please remember, then you need to find out what is the total strain energy. Same thing we did it here. So you can check. Same thing we did it here. So we did some of the strain energy in AC portion, strain energy in BC portions. Then I calculated what is the total deflections. This is how we need to do. This is how we need to find out the deflections by using strain energy method. Thank you, guys. Strain energy method. Thank you, guys.